Hi, welcome. My name is Gesa Bertrang and I'm a postdoc at MPIA in Heidelberg. Today I want to open with a question. Did we actually observe a young cousin to our own solar system? To take away the suspense, but maybe actually adding some, yes, quite likely we did. The disk I'm talking about is HD 69142. Just in case you should wonder, no, it's not the one in the D-sharp sample. This is the other HD69. This one is surrounding an Herbig AE star with 1.65 solar masses. And it's very close by, only 113 parsecs away. And this close vicinity allows us to point that with instruments such as SPHERE towards it and find these beautiful structures. You see here an inner cavity, a bright inner ring, a gap, and then followed by an even more substructured outer disk. When you now look at the ring, at the gap, you see it's a little bit elliptical, but this is perfectly fine because this is what we expect from a disk with some inclination like this one of 13 degrees. However, if you then look at the ring, it's clearly substructured. However, it's also clearly looking like a ring. And what we have here is the first detection of an intrinsically elliptical shaped dust distribution, which appears like a ring once it's projected by 13 degrees. Yeah, this was the first finding of such a feature, and we published this back in 2018. And when you now look at all these structures that we see, the question that rises, of course, what is causing it? And it's really tempting to go for protoplanets shaping this disk. We were by far not the first or the only ones who were looking at this disk. And when you go through the data, very exciting observation of this disk was done 3 years before ours in 2012, then published by Kwanzaa et al. 2013, done with VLT NACO. And this was at that time not only the high spatial resolved, now only beaten by our SIMPOL observation, but also in the inner ring, they reported a surface brightness dip. So it was, of course, very interesting to see, do we see something like that as well? And yes, around here, we actually see a surface brightness dip. Now let's go to the polar plots to make it easier to see. I'm going to show more of these. So I want to explain them. What you always see on the y-axis is the radial distance, and on the x-axis you see the azimuth angle given in degrees north to east. The blue shaded region in the lower panel that's showing the NACO data from 2012, you see the position of the surface brightness dip reported by Kwanzaa et al. And the solid line is indicating the center of this dip. And the blue region in our SIMPOL data in the upper panel is actually showing the surface brightness dip 3 years later. And as you see here, it's not on the same position. What you also see here is the increase of spatial resolution. But this led us think, what if this is actually the same surface brightness dip? Does it move with the Keplerian velocity of the inner ring? And we found, no, it's not, it's too fast for that. In fact, it has the Keplerian velocity of an object much, much closer in, about here. And we proposed that this dip is actually, or might actually be, a shadow cast by a protoplanet candidate surrounded by dust onto the bright ring. So with this proposal, we gained another round of sphere time. And this is what I want to show you now. This is our follow-up observation, again with the 3-year offset done in 2018. And we repeated the same observation. And what you see here is that the ring changed a bit. And to make it more easier to spot, I show you here the contour lines. This is the contour lines of 2015 SIMPOL observation. I show you here the center position of the dip in the NACO 2012 image. This is the center of the dip of the 2015, and this is our prediction for the 2018 position of the dip, the center position. And this is the contours of the 2018 observation. You see, it's not a perfect fit. However, given the uncertainties, particularly due to the spatial resolution in 2012, it fits very, very nice. So, what do we have here? Going back to the polar plots, we see the shadow moves systematically towards north. So the idea that the picture we propose here is actually we have a protoplanet candidate surrounded by a circumplanetary disk at about 12 AU. Unfortunately, this is within the detection limit of sphere, casting a shadow on the bright ring. In 2018, we published a very elaborate radiative transfer model fitting the spatial resolved optical and millimeter data as well as the ACD, and we trust in this model quite a bit. And in this model, we showed that the disk is actually pretty flat. So given that the disk is flat, we can use geometric optics to conclude from the size of the shadow, the dip width, over using the Hill radius onto the candidate's mass. And we deduce that the candidate should be something of 1 to 10 Jupiter mass. I'll show you a little bit later why we rather think that this is a 10 Jupiter mass than a 1 Jupiter mass candidate. If this is actually a shadow, then it should cool down the dust, right? And if the shadow is cast, it should cool down the dust also. It's a flat disk in the midplane, so we should be able to see it with ALMA. Luckily, there was a highly spatial resolved observation with ALMA of this disk. It's 2 times more coarse than our simple observation, but comparing optical to millimeter, that's quite good. The data was originally published by Perez et al. 2019. And as you see here, again, I marked the surface brightness dip in the ALMA observation as well in blue, and it fits perfectly well. On the left-hand side, you see the ALMA observation as it was done. It's a very beautiful structure. When you have a little closer look on the comparison of the optical and millimeter data, you find even more features. I want to point out 2 that I find very fascinating. The ring is not at the same radial distance. The ring in a millimeter is further out. It's actually 4.5 AU further out. And this is exactly what you expect from a pressure bump. So we spatial resolve a pressure bump in this disk. And then when you look at the shape of this ring, it also does not look similar. It does not look the same in the optical and in the millimeter. But we have in both wavelength ranges, we have a smooth and a fuzzy edge, and the fuzzy part of the ring is pointing towards the pressure maximum. And this indicates grain size dependent dust dynamics. Now, the architecture we propose for H1869142 is this. This disk is shaped by 3 massive planet candidates, a 10 Jupiter mass planet at 12 AU and 2 1 Jupiter mass planets at 35 and 45 AU. Only from the observation, multi-wavelength over time, we already have plenty of constraints. However, we also run HD simulations to test our scenario. These were particularly run by Anna Penslin, a PhD student of Willy Klei in Tübingen, and they include planet migration. And Anna was able to show that it's actually a 10 Jupiter mass planet that can create the inner cavity and also the inner rim of the ring. So this is why we think it's rather a 10 than a 1 Jupiter mass planet. And we need the 2 1 Jupiter mass planets further out to open the gap. One is not doing the job, and they cannot also be much more massive because we don't see any indication for them in the data. And 1 Jupiter mass planets are able to be hidden with the data that is now available. If you question the stability of such a system, we did too. So Trifonov here at MPIA run n-body stability analysis, and you see here all the stable orbits for these 3 giant planets. And what really fits, they really fit well into the dust distribution of the disk that we find. So it is, again, 2 more constraints that are supporting our hypothesis. So now, to conclude, did we find in HD 69-142 a young cousin to our solar system? Quite likely, yes, we did. The 10 mega-year-old HD 69-142 is most likely evolving into a system such as HR 8999, so a cousin to our own solar system. If you have any questions, I'm very happy to answer them. Write me an email, contact me in the sessions. See you. Thanks.